this month is actually one of our organizers, Mayuko. So we're very happy to have her give a talk on what she did her PhD on recently.
Yes.
So just a quick introduction. So Mayuko got her PhD in March of this year from the University of Tokyo. She's been working since then as a postdoctoral researcher at the Department of Multidisciplinary Science at the Graduate School of Arts and Sciences at the same university, University of Tokyo. And she specializes in observational studies of small-sized exoplanets in order to approach the fundamental question, why are we here? So she's also actively involved in science communication, obviously because she's a co-organizer of Space Cafe. She also has her own YouTube channel where she does a lot of cool videos, so please check that out, and other media. So Mayuko, whenever you're ready, please take it away.
So good evening, everyone. Thank you so much for coming tonight. I'm very excited to be here to present my research. So today's talk title is Spotting the Stars, the Impact of Star Spots on Exoplanet Exploration. So actually, I got the idea of this talk title by ChatGPT. I like this title. So it means it is time to think of or put the spotlight on to the stars again for the exoplanet exploration. So first, this is exoplanet. So maybe you already know, but the exoplanet means extrasolar planet. So it is a planet orbiting around the star that other than the solar system, other than the sun. So we already found a lot of exoplanets right now. And another important thing is star spots. Star spots is kind of spot similar to the sunspot, maybe you saw. And star spots is a place, specific area on the stellar surface that have a relatively low temperature to the stellar surface. The mechanism of star spots is related to the magnetic activity of the star, but actually its detailed characteristics or the detailed mechanism of star spots is still unknown. So there is a mystery of the star spots. So so today's topic of my talk is the relation between exoplanet and star spots. But how are they related? So here's the questions I need to answer tonight. One is why do we need to know star spots to investigate exoplanets? And the second one is how can we characterize star spots? Maybe you will find the answers after my talk, I hope. So let me introduce myself. So I am Mayuko Mori. I am one of the organizers of Space Cafe. So as Ken explained already, I graduated from University of Tokyo. Got PhD from University of Tokyo last March, and I started as a postdoc this April. And I am an observational astronomer. So sometimes I go to the telescope, or I use the telescope remotely to get data, and then after that I analyze those data. So I really like to go to the telescope or observatory and observe during the midnight. It's a very special time for me. And let me advertise my YouTube channel. I am running YouTube channel called Asnao Science, and in my channel I'm uploading the videos, some videos about the explanation, instruction or explanation of the astronomy or some kind of exoplanet science, and also I uploaded some videos about PhD life or researcher life, so vlog style videos. And also I sometimes do interview to the astronomers or planetary scientists. So if you're interested, please see my channel. Suddenly, unfortunately, all the videos are now in English, in Japanese, but a few of them have English subtitles, so maybe you can enjoy. And also, I really appreciate if you can help me to translate or put the English subtitles to my video. If you can help me, please let me know later. So let me start from explanation of exoplanets. So how many exoplanets have been discovered so far? Can you guess? Maybe 100, 1,000, 10,000. 1,000. So now it is more than 5,470 as of today. So I always show these slides when I do this kind of public talk, and this number is continuously growing. So maybe 2 weeks ago it was 10 or 20 less than this value. So in my sense, it seems like the number of planets is increasing 1 planet per day. So now it's a lot of planets are found so far. So now exoplanet science is gradually shifting from finding planets or growing the number of discovered planets to more detailed characterization of each system, planetary system. So this is a roadmap that is made from left to right. It shows the exoplanet research related spacecraft. So from Hubble, Spitzer, Coral, Kepler, Gaia, TESS, KELPS, and Webb is now working. Webb launched 2 years ago in the Christmas day, and then we will have Plateau and Ariel in the near future. So before, many spacecraft was made for the purpose of finding planets, and then also we have several spacecraft before, but from now and in the near future, the many spacecraft will be dedicated to atmosphere characterization of exoplanets. So atmosphere is one of the very important signatures of exoplanet that we can observe and characterize. But how can we see exoplanets? So maybe, so this is the picture I took in the Hawaii. It is Subaru telescope. But if you see the star, it looks like dot. But even if you use this kind of very large or largest telescope in the world, the stellar light is still a dot. So we cannot see any planet around it usually. So it is very difficult or impossible to usually see the light from exoplanet. So this is one of the very successful method to detect or characterize exoplanet. It is called planetary transits. So like I don't know, like it is as shown in this video. When the planet crosses in front of us, in between us and the star, host star, the light of the star becomes a little faint, or like this. When planet crosses in between us and the star, the stellar light becomes a little smaller. This fraction is just like 1% or less than 1%, 0.1% or so. But still we can see this kind of signal. So this is a transit. This is called transit method. So when we observe the stellar brightness continuously, then we can see this kind of dip in the light curve. Light curve is the plot of the stellar brightness according to the time. In the light curve, we can see this kind of 1% or less than 1% dip. So if we put transit depth according to the wavelengths, I will explain it later, it is called spectrum. So how about if we observe it with spectroscopy? Spectroscopy means like maybe you know the light can be separated into several wavelengths or several colors. It is very important in observational astronomy. Even if we see the same phenomenon in different wavelengths, then we can see different things. And it is very important to observe in multiband. So if we observe in transit in blue light, for example, if the planet have the atmosphere that absorbs specific wavelengths, at this point blue wavelengths, then the blue light coming from the star is also blocked by the atmosphere. So if you observe this phenomenon transit in blue light, then the shade of the planet becomes larger. Can you see? Then the transit depth will be deeper. But if you observe it in red light, which is not absorbed by the planetary atmosphere, then the transit depth is not that deep. Can you see? So if the blue light can be blocked by the planetary atmosphere, but the red light is not blocked by the atmosphere, then if you observe the transit in several wavelengths, then we can get this kind of figure. It is called transmission spectrum. The transit depth according to the wavelengths. So this time the transit depth in blue light is deeper than the red light. So this wavelength dependence have information of the planetary atmosphere. So in some specific wavelengths, the transit depth will be very deep because the atmosphere absorbs that specific wavelengths. So we can compare our observational spectrum and then atmosphere model spectrum, and then we can put constraint or retrieve the atmosphere of the planet. So for example, if the planet doesn't have specific amount of atmosphere, or atmosphere is cloudy, there is clouds in the atmosphere, then the wavelength dependence will be smaller. Then the atmosphere model should be also flat. If it has a lot of atmospheres that absorb specific wavelengths, then the transit depth will be varied according to the wavelengths. So we can infer or retrieve the atmosphere signal. So it is the very state-of-art telescope, JWST, and JWST got this spectrum of the exoplanet WASP-96b. So this is a kind of hot Jupiter, very hot Jupiter-sized planet, and maybe you know there you can see there is a wavelength dependence, and we can infer those wavelength dependence. We can infer from those wavelength dependence that the planet have H2O water in the atmosphere. It's actually water vapor in the atmosphere. So this kind of very but by the way, the difference of the transit depth here is just 200. This is 200 ppm. ppm is parts per million, so I don't know, 0.02%. Am I right? 200 times 10 to the minus 6 difference of the brightness, stellar brightness. So it's very small, tiny signal. But still we can see it with this kind of very new telescope. But here, then star spots becomes very important. Before in the transit, we just assumed that the stellar light is homogeneous, just kind of bubble. But actually, there is spots on the stellar surface. In that case, maybe you can imagine if the planet crosses in the middle of the stellar surface, if it doesn't blocked by if there is no spots and spots are located polar outside of the transit area, then maybe you can imagine the transit depth will be deeper here because the planet blocks the lightest place of the star. But also the brightness of the star spots, which we call contrast of the star spot, different according to the wavelengths. So this is very difficult to estimate the effect of the star spots. So actually, if there is star spots around the transit area, then the derived observed transit depth, wavelength dependence of the transit depth, also contains effect of spots, not only the effect of atmosphere, planetary atmosphere absorption. So it makes retrieval, atmosphere retrieval, very difficult. So we need to model spot distribution or spot characterization for accurate retrieval of planetary atmosphere. Actually, this is our research. There is some example that the planetary transmission spectrum can be interpreted as that has an atmosphere, or there is no atmosphere but only the effect of star spots working. So both model can fit to the same kind of feature in the transmission spectrum. So even if we see this kind of wavelength dependence on the planetary transmission spectrum, if we don't know anything about the star spots, then we cannot constrain. We cannot say the planet has actually atmosphere. So before understanding the planetary atmosphere, we need to understand star spots. So this is the image. Actually, it is just an illustration of a red dwarf K233. It is one of my interests. As I said, the nature of the star spot is still very unknown, but we recently knew that the star spot is relatively larger than the solar spot. Sun is usually very quiet, but other than the sun, the stars, most of the stars, a lot of the stars have a lot of very inhomogeneous surface. So it's very difficult to constrain their surface, but also it's very important to constrain their surface. So maybe now you already know why we need to know star spots. So it's very important to investigate transmission spectrum of stellar exoplanets. So the second question is, how can we characterize star spots? So again, stellar light is just a dot. Even if we use the largest telescope, we cannot see, oh, there is a spot. No, it's just a one light from the one dot. So how can we see star spots? So again, light curve, the stellar brightness variability is very important. When we do the monitoring observation of the star, the stellar brightness changes. Some of the stars, stellar brightness changes like a sine curve according to the time, which is interpreted as when the stellar light brightness is the most bright, then there is almost no star spots. But if it becomes very dark, faint, then there is a lot of the maximum star spot covering fraction. And then, as the star rotates, then the brightness changes. So the rotational period corresponding to the brightness variability period. So this is how we can infer the star spot distribution from the light curve. And again, multiband or spectroscopy is very important because I already said, like, the star spots contrast to the stellar surface different according to the wavelength range. So if we, in the blue band, the star spot looks darker than in the red light. So if we observe stellar brightness variability in several wavelength range, then we can see the several different amplitude of the stellar brightness variability. So this is important to constrain the spot temperature, actually. Our team has telescopes all over the world, actually. The one instrument is in Okayama. This is the first instrument which our group made, and the second one is Muscat 2 in Teide, Spain. Teide is in Tenerife Island, and the third one is Muscat 3 in Haleakala. So 3 of them can do the multiband photometry of the sky. And also our group has access to the LCO 1-meter telescopes. It also locates 5 places in the world. So these telescopes which are used is very useful for this kind of monitoring observations, because if we want to observe stellar brightness variability, oh by the way, this rotation period is around just several days or several tens of days, so it's kind of relatively short time scale. So if we do the monitoring observation, we want to take the star every like 3 hours or 4 hours, but from the ground only we can observe at night. So it's very difficult to get constant change of the stellar brightness. But then if we have telescopes in different longitude on the Earth's surface, then we can observe those stars like several hours per hours. So it's very important. So maybe you imagine when I say I'm doing the observations, you imagine I go to the telescopes, but actually recently, yeah, sometimes I go, but recently all the observation can be done remotely. So this is the website. So when I input like target position or time or exposure times, exposure numbers, then all of the observation can be done robotically, automatically. Then this is one of the data I have. K225 is my target. This is the star, just a dot. And we see the brightness. We can measure the brightness of this dot relative to other dots. Then we have this kind of, we always take this kind of images. So image and this is time directions. So after we measure the brightness of each frame, then we can get this kind of stellar brightness change, light curves. To get the stellar surface map from this kind of light curves, we need to make the spot model first, and then get light curves from this spot model, and then retrieve the stellar surface from this light curve fitting. Yes. So one of our target is K225. K225, oh, this is not mine. K225 is our target. It is a spotted red star. From the Kepler, the previous observations, we already know that K225 has a brightness variability. So maybe it has spot on the stellar surface. And also K225b is very important exoplanet. It is transiting South Neptune. South Neptune is the planet smaller than Neptune, larger than Earth, and it is good target for atmosphere investigation. So we want to use JWST or any other recent telescopes to get stellar planetary transmission spectrum of this target. By the way, South Neptune is very important target for our research because there is no South Neptune sized planet in our solar system. But there is a lot of South Neptunes outside our solar system, so we need to know why there is no South Neptune in solar system, but there is a lot. Actually, this is our light curves. From left to right, it is a different wavelength range. And we observed K225 using 5 different telescopes, 5 different wavelength range. Actually, 3 different telescopes: Sinistro and ZTF and TESS. TESS is the space-based telescopes, and others are ground-based telescopes. And this shows the colored dot shows the observational data, and this line shows the model which we fit best fit model to describe the stellar brightness variability. And you see the different of the stellar brightness change amplitude. So we can infer the spot signatures from here. So this is one of the very important discovery from our research. Actually, it is I haven't published the result yet, so I will write my paper. So these other colors dot from previous research, and this red dot is from our research on K225. And from previous research, they made an empirical relation from the stellar surface temperature and the difference of the temperature from spot and stellar surface. So it means if the stellar surface is 4,500 Kelvin, if the delta T is 500 Kelvin, it means the spot temperature is 4,000 Kelvin. So our research found that in a good precision, the spot temperature close to the stellar surface temperature relative to previous empirical relations. So this difference is very important because spot temperature is very important to infer the effect of star spots on transmission spectrum. So maybe from our research indicate that the spot temperature is close to the stellar surface temperature for cooler stars, maybe. So I want to confirm this, observing more and more cooler stars around here with good precision, using the same method which I used. By the way, am I very, is it okay? Okay. So this is our future prospects. So first, I want to do deriving typical spot features using observing more and more stars using the same method. Because as I said, we don't know the typical star spots. So we don't know usually spot size is small or large. Maybe it is too large for the sun, but we cannot deny it is possible for other stars. So we need to know the typical temperature, typical size, or typical distribution of the star spots. So it's very important to do these kind of observations for more and more targets to understand. Even it is very important to understand stellar magnetic activity because the spot is related to the magnetic activity. And again, it is very important for the exoplanet science. So I want to do the combination of spot characterization and planetary transit spectroscopy simultaneously. So maybe we can do the collaboration of ground-based telescope and space-based telescope together. So we can use ground-based telescopes to monitor the stellar brightness variability to confirm the spot distribution, and then use that information for the more detailed atmosphere characterization by space-based telescopes. So from this kind of combinations, maybe we can robustly discover the atmosphere composition of smaller size planet. Finally, so this is TRAPPIST-1 system, which is I really like because it has 7 Earth-sized planets orbiting around a red small star, and maybe in the near future we can observe the atmosphere of this kind of telescope, this kind of planets using JWST or any other near future telescopes. This is the imagination artist concept of TRAPPIST-1F. The F is this 1, 2, 3, 4, 5, fifth planet on the TRAPPIST-1, which is the TRAPPIST-1F is the Earth-sized planet around red dwarf in habitable zone. Habitable zone means probably life can be live here. So it's very difficult to define habitable, but may be suitable for life. So if it is very nice if we can get atmosphere information of those planets, and we are getting closer to detecting the atmosphere of this kind of habitable planets. But to do that, there is a lot of difficult point, and then understanding star spots comes first. So this is the end of my talk. Thank you so much, and I will take any questions.
Okay, thank you, Mayuko, for a great talk. So we can take some questions. So please raise your hand and I'll call it. Yeah.
Okay, so thank you for great talk. So I have two questions. First, you consider one star, one exoplanet passing in front of the star. What if some exoplanets passing in front of the star at the same time? Also, it depends on the distance from the star. The duration of the passing star is different, right? How to distinguish the
Yeah. Thank you so much. It's a very important question. It is possible that several planets passing in front of the star at the same time, but it's very rare event. Actually, we want to see this kind of event, so, but usually, so the orbital period of the planet should be different if there is several planet around the star. Before that, it is common to have several planets around one single star. It is called multiplanetary systems. It is very common phenomenon. But to the stable orbit, planets should be separated to each other. So it is the planetary orbital period is not that close each other. So even if they transit at the same time, that in the next transit, the transit timing is different. So in that case, we can identify the observing orbital period of each planet, and we can estimate, we can predict the transit time of each planet. So it doesn't matter. Yeah. And also, if the planet orbiting far from the star, then the transit duration will be longer. It is, it's very important to understand the planetary orbit. So what was your question?
So you can distinguish those experiments. Okay. But you need longer observation.
Yes, that's true. To observe this kind of, to define the observational, to define the orbital period of each planet, we need very long observations, and those kind of observations are usually done by space. So most of the transiting planets found so far was found by TESS or Kepler, which is the space-based monitoring observation.
Okay, thank you. The other question is about the star sports. That's really interesting. So the number is changing with periodicity, right? Let's say for 11 years for the sun, right?
Yeah.
Do you need to consider it?
Actually, yes. 11 years for the sun is activity cycle, but the star spot lifetime is shorter than the 11 years. So for like sun-like stars, the stars which have similar mass to the sun have very active spot appearing and decay. So we need to consider that. We need to take into account those effects to our model.
Is there any model?
Yes. Suppose emerging and decay. But actually, for the cooler spots, for like our targets, the spot lifetime is relatively longer, more than like 100 days. So in our observation, the spot decay is not that important. So maybe we can, we think we can ignore those effects.
Interesting. Thank you.
Thank you.
Jason.
Two things.
Yes.
Number one, the phrase you're looking for with the last question, planetary alignment.
Mm-hmm.
Alignment.
Yes.
Number two, when you're studying star spots, do you ever wonder if another planet is studying us and thinking, is there life on this planet?
Yeah, I sometimes think about that. And also there is a paper, actually published paper, which estimate the planet which can see Earth's transit. The planetary systems around the equator of the solar system. I think those kind of research is kind of very interesting, but maybe difficult to scientifically think about.
Yeah, question.
If a star has got multiple star spots, would all of those star spots have a similar difference with respect to the surface temperature, or would they be wildly different?
Yeah, we think so.
They'll
Yeah,
be
star
similar?
spot have a typical temperature. It is also observed in on the sunspot has a typical temperature, and from the simulations also it is supported. The idea is supported.
Relating to that question, I was wondering what is why the temperature is of your interest, because I thought like we are looking for the light intensity change, so that we can see if it's exoplanets passing or not. But then like you saw the figure of temperature, so I was wondering why is temperature is of your interest, right, as well?
Ah, okay. So
So-
temperature is just one result of our research, but so this kind of for this figure, we don't need planetary transit. It is just
Okay.
observing the stellar brightness change because of the spot transit, kind of.
Yeah.
So, yeah, we also know the spot covering fraction and spot distribution, spot location and size is also another parameters we get, and this is one important parameter.
Alright. So like knowing temperature also like helps you understand what's going on.
Yes. So because of the maybe I skipped, but what is very important is spot contrast, because this also affects to the stellar planetary transmission spectrum. Spot contrast is very important. Spot contrast according to the wavelengths is very important, and spot contrast is combination combined with stellar spot temperature
Alright.
relative to the stellar surface temperature. So it's very important parameter.
Alright, thank you. Thank you.
Yes.
So I have a couple of questions.
Yes.
First one, thank you for the talk. So the kind of planet, right? Does that affect the kind of planet? Like, is it like a gaseous giant or rocky planet? Does that affect any kind of observation
Rocky planet or-
versus gaseous giant
Ah,
like
yes.
Earth or like Jupiter?
Yes. So if we observe different types of the planet in the transit method, wait. So like, if the planet is gaseous, then first the transit signal will be larger, and also it has a large atmosphere. Then the transit depths will be different according to the wavelengths. But if it is rocky, then the first transit signal should be smaller, and transit depth variability also becomes smaller.
So is it possible to like determine like your target K225b? Like, do you know like what kind of planet is it?
Oh yeah. This is the sub-Neptune planet, so it is larger than Earth and smaller than the Neptune, and from the actually we didn't do this kind of research, but the previous research showed this one. Previous research showed the K225 is should have. Oh wait, it is a kind of long story, but sub Neptune should have atmosphere, a large amount of atmosphere from theoretical calculation or other observational facts. But K225b actually have flat-like transmission spectrum. So it is one motivation why I wanted to answer why it has flat transmission spectrum, which means no atmosphere or very small amount of atmosphere compared to its large size of the planet. So this is very, this is the reason K225b is very important, interesting target for the atmosphere research. And one explanation is that the mass of the planet, which is very difficult to measure actually, is larger than we thought. So maybe K225b is a little dense planet, so that the atmosphere is shrink. Then atmosphere signal is also small, but we don't have the very detailed transmission spectrum of this target yet. So that's why we want to observe it with future telescopes, future space-based instruments, and then we need the star spots.
Thank you. So, second question, can you show that slide with the different telescope data?
Yeah. This one.
Yeah, so I'm interested in a bit of like data analysis part of it.
Mhm.
So like the test which is on the space, like it has like the data is very much condensed in that the confidence of the interval,
Mhm.
confidence interval, but for the rest of the data, like for the Earth-based telescopes, like the data is like quite different. Like
Yeah.
I guess like there are a lot of factors now, like atmosphere, satellites, and other than like how do you determine like what kind of like the processing of the data like into information?
Okay, so actually, yeah, well, this is a space-based telescope data, so it has very dense cadence of the observations, and also the observational error is very small. And others are from the ground-based telescopes, and it has a large uncertainty, and there is a white noise on the data set. It is mostly because of the Earth's absorption of the terrestrial Earth's atmosphere.
Yeah.
Yes, and also there is maybe instrumental noise and yeah, and also the we need to.
Yeah, so the question is like how the data analysis happens, like even with all that noise, like I know several reasons, but how the data analysis happens even with all that noise.
Okay, yeah. In this method, we use Gaussian process. It is a statistical method to get the best mean of the data set, observational data set, and the Gaussian process also account for the white noise, which is the noise that doesn't correlate it with any other time or other covariates. So we also consider that there is okay. In our analysis, of course there is a noise that is correlated to the planetary Earth's atmosphere or like the altitude of the star or those kind of things. But it is difficult to get those kind of information. So we first fold all the light curves into stellar rotational phase, and then use those kind of noise as a white noise in this kind of phase folded light curves, because those noise cannot be related to the rotational phase. So after phase folding, we can just use those kind of noise as a white noise. not related to their rotational phase. And then we can model the brightness variability accounting that white noise. Did I understand? Did I answer your question?
Yes.
Thank you.
So you talked about color, different color of light to detect in order to understand what is included in the atmosphere of exoplanet.
Yes.
And can you explain, for example, in order to detect H2O, which color do you use?
Okay, usually we use, recently we use infrared, so redder than red. But, sorry. So this is the example of the very recent data set, and it has H2O features. So this kind of feature can tell us if the planet have H2O in the atmosphere, and it is 2.0 microns, so we cannot see this light actually, but the wavelength range is also very small, so it's very kind of, but
So this,
very different, small difference of the wavelengths in infrared.
okay, so that x-axis, the horizontal bar, is this not the type?
This one is the color or wavelength.
Oh, okay, so it's kind of outside of the red that we can observe with our eyes.
Yes.
That is kind of 0.75 to 2.75. It's kind of infrared.
Infrared wavelength range.
Yeah.
Around here, maybe the optical light, visible light.
Then, so the blue that you mentioned is kind of also ultraviolet side.
Actually, the illustration I showed is just the illustration. So we use for our research, actually we use optical light, visible light. But usually in the space-based telescope, we use infrared, because in infrared there is a lot of molecular features. But actually, optical light is very important to constrain spot signatures. So if we can get very wide wavelength range data from optical to infrared, it's very nice.
Okay. This is another big mystery about the color.
Mhm.
Thank you so much.
So short question.
Yes.
Related this question. Okay, so what is the observable color? Observable wavelength? Like we have radio to X-ray, very red to very blue, right?
Yes.
Yeah. What is the observable color?
Any color can be yes,
Even
observed.
X-ray.
Yes, but for exoplanet science,
Yeah.
for this kind of research, usually we use optical to near infrared.
How about radio?
Radio, maybe that's possible, but in the radio observations, I don't know what kind of features or what kind of molecules or any other atmosphere signals can produce features in radio wavelength range. Yeah, but also there is some attempt to do this kind of transmission spectroscopy in UV, and in UV we can see the hydrogen signature. So yeah, different wavelengths can see different molecule or different elements in the atmosphere. So it's very interesting. Thank you.
Can I just add for something for both?
Yes.
Actually, don't think so much about the color, because color. So this H2O curve, that's a really good example of looking at data, not the color itself, because color is not the super important aspect of observations.
Yeah, actually no color.
Yeah.
Yeah.
Are there any more questions? Okay, then I think.
Can I have the last question?
Sure.
Yeah. Thanks, Michael, for the nice talk. And I also didn't know you're using LCO. Yeah, which is because I'm in the steering committee this year.
Oh.
And what do you, so since you just finished your PhD, what do you actually want to keep doing in terms of like long-term studies?
Okay. Yes. So first, I want to I made this kind of method in my PhD, so I want to apply this method to more and more stars. So now I have 40 hours or 80 hours LCO time next semester. So I will do the monitoring observations of 10 or more stars other than K to 25. So we can get the typical star spot signals. And also, I really want to apply our method to the space-based telescopes and to get observing time of the space telescopes. Actually, to propose observations using JWST or any other space-based telescope is very difficult. We cannot get observing time on these kind of fancy telescopes, but eventually I want to get this kind of transmission spectrum by ourselves, and then retrieve atmosphere signal and planetary the star spot signal at the same time simultaneously. So this is my dream. Thank you.
Okay, so I think we'll end there, and then we have a few ending slides. Okay, so thank you again, Mayuko. This one? Take it off your fingertip.
Okay.
Or you can flip it.
Okay.
You
Okay.
guys do it.
Okay, okay, yeah, so thanks again for coming. We are Space Cafe Tokyo. We hold events here at Good Heavens almost every month. So next slide. So yeah, thank you again to Hisako and the rest of the staff here at Good Heavens. Please, yeah. Yeah, we've had a good relationship for a while, and we've been hosting this event here for several years. So please follow them on social media. Next slide. So yeah, just to advertise a few of their events coming up. On August 6th, they have a charity pub quiz, and August 9th, they have a live acoustic event. And that's going to be, those are both at night, I believe. Yeah, here. So yeah, if you're interested in those, please come on those nights. Next. Okay, so actually an event that is happening tomorrow night in Kawasaki is Nerd Night, so they are kind of like our sister event. It's a similar format. They have 2 to 3 speakers though, instead of just one, and they talk about a variety of things. I think their thing tomorrow is they're gonna have one person talk about aircraft, like electric aircraft, and their second talk is going to be about music and dementia drawings. So see, it's very diverse, but this is also a very cool event. I recommend you go if you have time. So again, it's tomorrow night in Kawasaki. Next. Okay, so our next event, we haven't quite settled on a speaker or date yet. We might end up skipping August, it looks like, and it might be in September instead. But please follow us on social media and to keep up with announcements. And it will be, of course, here at Good Heavens at the same time. So follow us. Okay, thanks. So follow us on social media. We're on Facebook, Twitter, Meetup. We also have a YouTube channel. So this tonight's event will be eventually posted as a YouTube video. And if you have not done so yet, please sign in using the QR code there. And yeah, so the Space Cafe Tokyo team, so I'm Ken, Mayuko you just heard from, and Tilina over there, and our photographer Chase. So thank you again. Please feel free to grab more drinks and food. Stick around, ask Mayuko more questions if you had more you thought of, or interact with anyone else here. And hopefully we'll see you again maybe next month, maybe September. Okay, thank you.